This one's a little bit different the way it moves forward, but I think we're set. So this should be Carb Lecture 1. This is where we left off last time. We got through the first part of this. We talked about all the wonderful carbohydrate sources there can be in the diet. And the point of today is we're going to now kind of go down to the level of the molecules. We're going to look at the details of the structures of the three main monosaccharides in the U.S. diet. And we're not going to relive all your great memories from organic chemistry and things like that. We're going to just stay on some of the important points. And we have to know the structural details to a certain point because it involves their metabolism. Okay? Then after we go through that, we'll talk about digestion, absorption of the carbohydrates, and then we'll kind of start following the carbohydrates around and their metabolism in different tissues. And then we'll kind of get into glycolysis and pathways, but mostly in here we're going to focus on the regulation of those pathways. So then the point of that is then we're going to learn the carbohydrate in structure and storage and metabolism, and then we're going to branch out. Then we're going to add lipids to that, and then we'll start putting them together. And then at the end of the quarter we'll do protein, and protein's different because it's not a significant energy source. So that's mostly about different functions of proteins in the body other than energy. Okay? Any questions on this one? I think we went through all the details on this slide. And we stopped there, right? Okay, so these are the structures. And I mentioned before that there's three main monosaccharides in our diet. And even though probably for the most part we consume them as complex carbohydrates, they're still broken down into the monosaccharides for absorption. And we can look up at the top. I showed you that formula before, and I said that these are the three main monosaccharides, and they all have the same formula at the bottom of this slide. But I said their structures are different, and that has consequences in the body. So we can see the first two, glucose and galactose, they look really similar. They're both six-membered rings. And they have 6 points to their ring, but remember this one, that oxygen bridge? We're going to talk about how that's formed today. And so you've got 6 carbons, but this carbon, the CH2OH group, is outside of that ring. Okay? So in orange is the difference between glucose and galactose. That's the only difference. So you guys are going to relearn how to draw these structures, and I'll show you how. And remember, if you know glucose, for galactose, all you have to do is flip that. That hydroxyl group is on the opposite side of the carbon. And so just think right away, for glucose, that hydroxyl group on carbon number 4 is down. For galactose, it's up. That's the only difference. And over here, black sheep, fructose, right? And fructose is 5-membered ring, even though it has 6 carbons. And what we'll see is it's the position of that unsaturated bond, that double bond, I should say, that double bond in the structure that makes it form a 5-membered ring instead of a 6. So when you draw this one, we'll just pay attention to that. But still, there's an oxygen bridge right there. And that's what's linking carbon 2 and carbon 5. Now, why does that matter? Well, because the differences in structures are recognized by things like transporters and enzymes. They don't always treat them differently, but they definitely recognize them differently. In other words, transporters can tell, what they're transporting in general, and we'll have some good examples of that as we go through metabolism, but that can determine whether or not these guys get inside cells or not. Remember, these are water soluble. They need membrane transporters to get in and out of cells. So that's going to be a big part of what we learn. And then also enzymes, of course, are often very specific to their substrate. So we'll look at that. And one of the interesting things about this is the taste properties. Which one of these is the sweetest? Fructose? Yeah, be confident even if I question, right? Yeah, fructose, right? And that's one of the reasons why we see fructose in a lot more food items than you would expect. But if we look at this and if we say, what's the relative sweetness of these? It's kind of interesting, and this will explain things like high fructose corn syrup a little bit. Is high fructose corn syrup bad for us? Who says yes? Who's just as bad as what?
Is anything else? Like, I think that high fructose corn syrup is just as bad as sugar. You're saying that sugar's bad.
Yeah, what's the difference between sugar and high fructose corn syrup?
The ratio of like fructose to glucose.
Is there a big difference in the ratio?
It depends. It's like 70-30 usually, right?
Yeah, so you're on the right track. They're actually very similar. Very similar, and I'll explain that in a second, but a lot of people think, oh, you know, fructose, eliminate it from your diet. I don't think you have to do that. It just has to be eaten in moderation, right? So let's look at why that's one of the more popular items in foods. But so we should be concerned with it, but we have to also qualify those concerns with, you know, kind of evidence-based findings on what we're doing there. So let's see, I think I have a chart that will show, let's put our many people's favorite carbohydrate up here first. Sucrose. And what's that made out of? Glucose and fructose. We're going to say that's our standard. We're going to say this, we're going to set this at 100%. This is just relative sweetness. What about lactose? What's that made out of? Glucose, galactose. No fructose in there. Less sweet than sucrose. I think we'd all probably say, yeah, I think so. It's about 16%. It's a big difference, right? Have you guys had lactated milk or any of those products? That's what I drink. It's sweeter. It's more sweet. Why? Because this has been converted to glucose and galactose. So you get more of a sweetness effect because of that. So people that use that maybe you could say, oh, that's great. They use less sugar. You don't have to, right? So that's one thing to think about. Maltose, I'm not even going to put up there. How about this one? Wow. What's my percentage here? More than 100%. It's glucose. Now here's an interesting one, galactose. A few years ago, I was formulating a sports drink for a company, and I said, what are my limitations? They said, you got to put galactose in there. So I had some students, God love them, they tried all these different formulas with me, and one of the things we realized, wow, galactose doesn't taste good at all. Neither does maltodextrin, horrible. They all survived. Their palates permanently affected, but we got through it, right? So a lot less. So far, which one are we missing? Fructose. Now, what do you think? Higher than this? That's sugar. Who says, yeah, probably higher than that? Who says, no, that's not as sweet as sucrose? It's sucrose. Almost twice. It's almost twice as sweet as sugar. Okay? So this, we're going to say is, how should I put this? 50% glucose, 50% fructose, right? For every molecule. It's high fructose corn syrup. What is it? Where does it come from?
Corn.
Comes from corn, right? Is you take basically the starch and you basically concentrate it and you put it in solution, and that's the syrup. And what's starch made out of? It's all glucose. So how do we get here? This is high fructose corn syrup. Acidic and enzymatic conversion of glucose to fructose. So you take that glucose and convert it to fructose. Is that easy? Yeah, it's pretty simple, very cheap. And then you go from glucose to fructose. Now you've got a very sweet molecule. There's two major forms of high fructose corn syrup that you find in foods. And the most common one is HFCS 55. That means it's 55% fructose. Pretty similar, right? As sugar. So we do want to watch that. And so you find sucrose in a lot of stuff, but you also see that in a lot of items. It's a preservative, but it's also a sweetener. So in processed foods, there's a good chance it's in there. I think they're making a kind of progress in having less of that in certain things, but you do have to watch the label. And the reason I say that is you have to realize, these are calories. It's a sweetener, but there are calories. And fructose is metabolized differently than glucose. So we're going to talk about that. We'll talk about the effects. We should have some fructose in our diet, but we want to kind of modify the amounts. And so I think we can kind of argue it's okay to have some fructose, but it's difficult to argue that we need to add more sucrose to our diet to get it. Okay? Here we are. This is the slide you've been waiting for, right? These structures again. And there's at least one typo on here, right? We've got anomeric carbon, we've got carbon number, and the aldehyde is spelled wrong, right? It's not part of a carcass. That should be HYDE, aldehyde, right? That's the group. And remember the aldehyde group? We all got this? And this kind of shows it up there, but this is an aldehyde. So if you look at, here's glucose, two different forms of glucose. Remember this open structure? What do we call this? Yeah, Fisher projection or Fisher structure. Some people say open chain, things like that. The point of this is you don't find the carbohydrates in this form very often in nature, but it helps us look at their chemical groups. So you'll see it like this. In solution, these guys are going to tend to form cyclic structures. And once they form that cyclic structure, they can actually open and reform. So they can sometimes flip. We'll talk about the D and the L in a second. But if you look over here, here's fructose. And it has that's a ketone. So this is an aldehyde. And if we look at the ketone, there's your ketone. And that's the difference between glucose galactose versus fructose. And what we're going to talk about in a minute is it's actually the interaction between this hydroxyl group on the highest numbered chiral carbon and that carbon that has a double bond. That carbon, because of the orientation of its electrons that it's sharing, is susceptible to nucleophilic attack. Remember that? You don't have to remember all that stuff, but essentially what that means is that double bond makes this oxygen able to then come in and form an oxygen bridge. So if you just look at it right away and go, oh, okay, that means this carbon number 5 and this carbon number 1, I'm going to have an oxygen in between that. And then if you go back to this, carbon number 1, carbon 5, there's the oxygen. That's why it does that. So it'll almost always form that structure. And then if you look at fructose, see the way it's different? Now that oxygen bridge is between carbons number 2 and 5. So let's look at why that happens. Here's carbon number 2, and here's 5. This oxygen is going to attack that carbons and electrons. And so you're going to get that bridge between 2 and 5. That's the difference. But that difference in structure changes their metabolism. Can we eat fructose and make glucose? No. What do you think? I'm pausing, wait. Yeah, he must be thinking, yeah, it's magic, right? Our body can actually convert the three. We can interconvert those three monosaccharides. And we'll look at the pathways on how that works, but that's why I didn't mind putting galactose in that drink, because we can convert it, and the liver can do that. All right, a couple other things on nomenclature here. What does chiral carbon mean? Chiral carbon has 4 different chemical groups attached. So you want to remember that, write that for me. And now what that means is, if we go through here and we identify the chiral carbons, we're going to look for the highest numbered chiral carbon, because the cyclic structure is dependent on an interaction of the hydroxyl group at the highest numbered chiral carbon and the carbonyl function. I'll say that again in a minute. Okay? So let's find the chiral carbons. This one's not. So we got 3 groups attached. This one, carbon number 2, is that chiral? It is, because you count this as a unique chemical group. It's got a hydroxyl group, it's got a hydrogen, and then it has this. That's considered a chiral carbon. 4 different structures attached. 3 is, 4 is, 5 is, 6 is not. 6 is not because it's got 2 hydrogens. So it's only got 3 different groups. Okay? That's why this hydroxyl group is in red. This is the highest numbered chiral carbon. That's the hydroxyl group associated with it. Okay? The other reason that's important is, if you have this structure and your hydroxyl group on glucose is to the right, that's its D enantiomer. Remember that word? We're just going to simply say enantiomers are mirror images. An enantiomers are mirror images of one another, or each other. I don't know the best way to say that. Right? In other words, if you take these two, it's like you put a mirror in between them and you were looking at their images like this. But if you look at this, the hydroxyl group is on the opposite side for the L form. And all the other chemical groups are flipped as well. All the chemical groups are flipped, including this one. If the hydroxyl group is to the left on the highest number chiral carbon, it's L. Now remember, that changes the structure. So it's metabolized differently. So I want you guys to memorize the structures of the most relevant forms, and that's the D form. So the L forms here are just for fun. You don't have to memorize those, even though it's just a simple flip. And the reason is because the D forms of carbohydrates are the most common in nature, and they're the ones recognized by us. Okay? So you want to memorize, you want to be able to draw this structure. D-glucose, and D-fructose, and D-galactose. Okay? And remember, if you look at the difference between glucose and galactose, all you're going to do is change that hydroxyl group. That's it. So my recommendation would be start with glucose, relearn that one. How many of you guys drew those before? Okay. So just relearn that really quick. Probably go through that, take you 5 minutes to learn glucose. Flip it, and you got galactose. And then fructose, you just have to make a couple adjustments. So let's look at this, unfortunately. So this is from 6th edition, I think.
Should we know both Fisher and
Yep. Yeah. So far you have those. Now let's look at this one. I'll tell you a few other details and the rest of the molecules you need to be able to draw. We look it up at the top. That's D-glucose. And I have that drawn in red because that's a typo. It's not a hydrogen there. They left the hydroxyl group off. That's what that means. Okay. So let's go through here and go, okay, let's see here. That looks like it did on the similar page, right? It's to the right, so we know it's the D form. And if we look over here, we're going left to right. This is showing that interaction between the hydroxyl group and that carbon. This carbon has an asterisk because that is the aldehyde group. In other words, you ever heard this? This is the carbonyl. In other words, sometimes it's termed as the functional group. Those all mean basically the same thing in this context. So in other words, that aldehyde carbon is the one that's involved in this oxygen bridge formation. Okay? Now one of the reasons that's important is because when you form that cyclic structure, and this becomes now a flat cyclic molecule, you have to pay attention to where those hydroxyl groups end up. Remember this? So there's a couple general rules here. One of the rules is, just remember this, if the hydroxyl group is to the right on the Fisher, it's down in, how do you say that? Hayworth? I generally say Hayworth. If the hydroxyl group is to the right in Fisher, it's downward in Hayward. So right equals down. So we kind of go through and we look at this. Let's go with carbon number 2. See what's to the right? Carbon number 3 is to the left. 4 is down to the right. 5 is down. Now 5 is a little bit different because your hydroxyl group is no longer there. That oxygen is part of this. Okay, so let's look at the last one. Here's simplified Hayward. Did you draw those? Would you draw this one?
Yeah.
Okay, you can draw that one, that's fine. If you want to use simplified, that's fine. Here's a little bit different. We're going to use the biochemistry nomenclature rather than the organic. The organic chemistry, when you see a straight line like that, what does that mean? That's a methyl group. We're going to say that's a hydroxyl group. Because I like biochemistry better than organic chemistry, I guess. But yeah, that's, yep. Now, so you can draw simplified if you want. If you draw Hayworth, just be consistent. Make sure that, like for example, if you draw a line like this and you have a hydroxyl group, make sure your line goes through that. Because if you're putting hydroxyl groups on this end is a hydrogen. So make sure you go through that carbon when you're supposed to. Okay? Now let's talk about this one. In other words, why does this say alpha? You just wrote on there, right? Your shortcut is right equals down. So you can add to that and say right equals down equals alpha. So let me explain kind of what's going on there, and then you can just remember this hopefully pretty easily. So when this cyclic structure forms, now I drew it up like this. And so imagine in this group, let's say this is glucose, and now that oxygen is going to be kind of attacking this carbon. When that happens, these chemical groups can be in this orientation, or they can be flipped. If it happens when this oxygen is on this side, when it forms the cyclic structure, that's going to be downward. If the attack happens when this oxygen is on the other side, it's going to be up. In other words, the hydroxyl group that's going to be left there can be either up or down. right? Because the hydroxyl group, when this oxygen binds here, the oxygen forms a hydroxyl group with that hydrogen, and we're going into a little bit more detail than we have to, but and so that's how that forms, and so you end up with a hydroxyl group here and an oxygen bridge. That hydroxyl group can either be to the right or to the left, like it's shown here, and what that means is if it's to the right, it is down. If it's to the left, it's up. If it's down, it's alpha. If it's up, it's beta. So another term for this is, remember the term anomeric carbon? The anomeric carbon is essentially the carbonyl carbon when it's in cyclic form. That's all that means. So all you have to remember is, for glucose and galactose, the anomeric carbon is carbon number 1. And that's the one you have to pay attention to, that position of the hydroxyl group. See the way this is alpha and it's down? Look at the beta. Beta D-galactose, it's up. Could this be alpha D-galactose? Yep. Does it function the same? Yes. Yeah. So that's kind of the interesting thing of this is, like when we talk about glycolysis and we say, okay, glucose is at the top. Well, what kind of glucose? Well, we know it's D-glucose. We also know it can be either alpha or beta. Doesn't matter. That glucokinase or hexokinase or enzymes that recognize that, they'll work with either alpha or beta. Okay? So a lot of times it doesn't matter. I'll tell you when it does in a minute.
So when we, or like if we ever need to draw these, will it be specified whether it's alpha or beta?
Yep. Okay. Unless I've forgotten and left it off, but I'll always try to ask you alpha or beta. Yeah.
So I'm assuming it's also the same for fructose?
Yeah, same thing. Well, fructose is a little, yes, in general. I'll tell you a couple of exceptions. Yeah, so here's one thing with fructose is remember, remember if you want, you can learn how to draw this, and then you can remember how to draw this, and then you'll have D-fructose in Fischer and cyclic form, and then you just have to take care of this, the beta or the alpha. Now, fructose is a little bit different because this is carbon number 1. And if we backtrack and we go over here, well, carbon number 1 is not involved in that oxygen bridge. Carbon number 1 has 2 hydrogens and a hydroxyl group. So over here, carbon number 1, this is the H2OH. Okay? This is not the anomeric carbon. The anomeric carbon is carbon number 2 in fructose. Carbon number 2, carbon number 2, carbon number 2. And remember that it's the anomeric carbon that can have its hydroxyl group up or down. So in other words, this is beta because the hydroxyl group on carbon number 2 is up. No one got that? So it's this hydroxyl group that matters, not the hydroxyl group that's attached to carbon number 1. Everyone have that? So for fructose, it's the hydroxyl group on carbon number 2, its position that determines alpha or beta, not the hydroxyl group that's part of carbon number 1. Yep.
Is the reasoning for that simply because that's the first one on the ring? That's why it's number 2 instead of number 1, which isn't part of the ring structure?
No, they number them here. Is that what you mean?
Well,
Yeah,
I'm
that's,
just wondering why it's it's the anomeric carbon because it's double bonded to the O.
yeah. Anomeric carbon because it's the carbonyl function, carbonyl group. It's where there's a double bond. That's what determines the carbonyl group. So you can say this is the carbonyl carbon. When it turns cyclic, we tend to refer to it as the anomeric carbon. They're essentially the same. It's the same carbon, just different structures. Remember all this? Okay. In a good way, I know. Now, here's the point. One of the things I said was be consistent. Now, remember, there's a hydroxyl group here. So don't just draw this line like this and stop. If you're drawing it like this, don't put CH2OH here and put a line here and stop. You got to fill it. You got to have a hydroxyl group there. Okay? And again, I can say alpha or beta. It'll always be D, but you need to be able to draw the alpha and beta forms on all of these. And that's essentially it. So you need to draw 6 structures. All right? And then be able to make them either alpha or beta. Oh, the other point. There's no OH here. So don't put a line through here. There's no OH here. That's a hydrogen. That's what I mean, be consistent. So if you look at this, any place where there is just the end of a line, if you're drawing the Hayward, that's a hydrogen. So don't forget this. In other words, don't stop your line right here, or that's wrong. Got it? A little bit more fun with structures here. All right, so those are the monosaccharides and their most important structures for us. So now let's talk about how these combine. Yep.
On the test, will you accept Hayward or simplified?
Yeah, as long as you're consistent. Yeah. No hybrids. Yeah. Okay. So now let's talk about how they link and then what we call those bonds and why they're important. So kind of the next step to this. Disaccharides and oligosaccharides, they contain monosaccharides of between 2 and 10 monosaccharides linked together. Right? Any more than 10, we call them polysaccharides. Okay? These are linked through acetyl or glycosidic bonds. I tend to say glycosidic. And the bonds can be either alpha or beta depending on its position before bonding. So again, that's kind of why we're going through this, is so that we can look at, let's say for example, a disaccharide and say, oh, that's sucrose based on its structure. And you want to be able to draw these as well. And since you know the monosaccharides, this is easy. And then we'll talk about reducing sugars. You ever heard that? Yeah, that's just a term we're going to go through really quick. So let's look at these. Maltose, right? Pretty common disaccharide in the diet. Not as common as sucrose. But maltose is glucose. I told you that before, right? On that other kind of the tree that showed the different forms. We've got maltose, which is glucose. Let's look at the bond. In order to name these bonds, you have to identify the anomeric carbons and whether or not that anomeric carbon is in the glycosidic bond. So kind of the first thing you do is, let's find the anomeric carbon. Well, glucose, it's right here. And if we look at this glucose molecule, it's right here. So this anomeric carbon is involved in this glycosidic bond. Okay? Now remember, this is the hydroxyl group that's now part of this bond, this glycosidic bond. So this hydroxyl group could have been up or down. If the bond is in a downward orientation, it's alpha. So to name this, we would say, oh, I found the anomeric carbon. It's in a glycosidic bond. Downward orientation, I say, it's alpha. This is carbon number 1 in glucose. So we say alpha 1. I tend to write it, and most people do, I think. Alpha 1, comma, 4. So you're basically indicating the carbons that are involved in the glycosidic bond by numbering them. Right? The comma indicates the other monosaccharide. So you're going to say alpha 1 to 4, because this is carbon number 4. Got that? What if it was Beta 1 to 4 is a different disaccharide. So the disaccharides are specific to their monosaccharides and the glycosidic bond. And the reason one of the reasons it's so important is nomenclature and enzymes and transport, especially enzymes, recognize that. Enzymes are let's say an enzyme is going to cut this. And we can imagine that enzyme's name is maltase. Maltase is looking for the monosaccharide components and the direction of the bond. Yep.
Even though maltose is always alpha bondage, that one is beta form just because the anomeric carbon is beta in that case?
Yeah. Is that what someone else is going to ask? Oh.
Anomeric carbon of the right molecule.
Okay, so we got that alpha 1 to 4. And now why does it say beta form? This is referring to the orientation of the hydroxyl group on the open anomeric carbon, which is this one. Hydroxyl group is up. We know up is beta. If this hydroxyl group was down, it would be alpha. In that case, is it still maltose? Yes. So most enzymes are going to distinguish this glycosidic bond. They're going to distinguish what the monosaccharides are. That's going to help them fit in that active site. But most of them they'll work with either alpha or beta here. Everyone got that? One more term here. Because this is a open anomeric carbon, this is a reducing sugar. Remember that? So these carbohydrates with open or unbonded anomeric carbons are reducing sugars. And what does that mean? That means that this hydrogen can dissociate this and contribute its electron to another molecule and reduce it. That's why they're called reducing sugars. That's all that means, is that hydrogen will come off. And as in the body, it's not that relevant for like things you do in the kitchen with foods or processing or chemical reactions, stuff like that. That's more commonly where you'll see that, but that's why they say that. So it's important that we at least know that. Okay? So the middle one is more fun with typos, but let's go through this. This is lactose. So we know the lactose is galactose and glucose. So here's galactose. It's anomeric carbon. It is in the glycosidic bond. And here's glucose. Its anomeric carbon is not. So some similarity to this, different monosaccharides and a different orientation here. So this one, it'd be better if they drew it a different way for me, honestly, but this is lactose. So again, we're going to find the anomeric carbon. We're going to say it's up. So that's beta. It's carbon number 1, so we say beta 1 to 4. And again, I would say it's better if they would have went straight line here. Straight line there. Because when you see that angle in some of these structures, what do you think?
Carbon.
You think carbon. It's not a carbon there. So in other words, it would just be a straight line here, a straight line there. Just as long as you draw it like that, then I know that you understand, oh, it is a beta 1 to 4. And remember, this hydroxyl group is always down. That's what makes it glucose. This hydroxyl group is always down. That's what makes it glucose. If it was up, it's galactose. Uh-huh.
Will it be okay if you do like a rounded?
Yeah, that's fine. Yeah,
Instead of like a sharp.
yeah. Yeah, that should be fine. What's wrong with this? This is beta form. Here's what we're looking at. Right, that's down. This should be alpha. So this is lactose alpha form. Good. So these are reducing sugars. Here's sucrose. And this one's a little bit different. Sucrose is different because both anomeric carbons are in the glycosidic bond. All right, so we have the three most common disaccharides. Sucrose is unique. I guess for two reasons. It's the only one with fructose. And both anomeric carbons are in that glycosidic bond, so it changes the nomenclature a little bit. So here's glucose, anomeric carbon, downward orientation. This is carbon number 1, downward orientation. It's bound to carbon number 2 of fructose. And remember, this could have been flipped either way as well. So if we look at this one, right, probably the most common way to refer to this is alpha 1, comma, right, alpha 1, comma, beta 2, right? Remember, the anomeric carbon could have been either way, it's up. And that's the carbon number 2. Alpha 1, beta 2, glucose, fructose. Alpha 1, comma, beta 2, glucose, fructose. Probably the most common way to name that glycosidic bond is sucrose. Is it a reducing sugar? No, because both anomeric carbons are in that bond. Good there? Yes?
Are you expecting us to put glucose fructose, or will we left off if we put sucrose in like the nomenclature?
You should put glucose, fructose. Yeah. Yeah.
So it's like the full way to like write these out, like for maltose, like with like the alpha 1,4 beta form. If you're looking like for the full name, or is it just like how we're like what's like the orientation of the
Yeah,
bond?
for those for maltose and lactose, yeah, for maltose you can say we can just say I guess you can say glucose, glucose. All right. Alpha 1 to 4. Glucose, glucose.
Okay, but then do you need to like say like that it's in a beta form?
Oh yeah, sorry. Is that what you're? Yeah.
Yeah, like the
Yeah.
like full.
Yep.
name form.
And if I ask you to draw the structures, I'll ask you alpha or beta form. Yeah, I'll indicate this. Sorry, I missed that. I'll say draw the structure of maltose. You know, and in the beta form or alpha form. Mm-hmm.
So you pointed to the glucose on the right in maltose, and it's in the beta form right now, but if that hydroxyl group was switched to the alpha form, it would still be maltose beta because or would it be maltose alpha? Because the glucose on the left is alpha because it's pointing down, but the whole glycosidic bond is beta because of the glucose on the right.
No, you say this is it's the beta form of maltose. So in this case, so your bond here is still alpha 1 to 4. Right, so you would say so maltose, you would draw this alpha 1 to 4. If you want to name it, you would say alpha 1 to 4 glucose, glucose. And then you would indicate alpha or beta form.
So the glycosidic bond has nothing to do with the form of the disaccharide.
Has everything? Yeah, it does. It does. The difference is, I guess, so maltose has 2 potential structures. So it could be alpha 1 to 4, glucose, glucose, beta form, or alpha 1 to 4, glucose, glucose, alpha form. Everything's the same except this is flipped. Both of those are maltose. Glycosidic bond the same.
So maltose always has an alpha 1,4 glycosidic bond.
Yes.
Okay.
Is the first two reducing?
Yeah, these two are reducing sugars because they have an anomeric carbon that's not in a glycosidic bond. Good there. That might take, if you just write that out a few times, hopefully it'll click. Next time we can go back through that as well. Yep.
So it's the beta form because of the unbonded carbon on the right side of the, right there. That's why it's beta form.
That's an anomeric carbon that's not in a glycosidic bond.
And it's going up, and that's why it's beta.
Yeah.
So for lactose, the form would also refer to the glucose on the right,
Yes.
not the bonded one. Okay.
Correct. It's always that open anomeric carbon. Good. Probably a good stopping point. So we'll take a break there. Yep.
So
Okay.
with sucrose, that's the only form, right? Possibly.
Yes.